Hello and welcome to Math Age. Today I want to look at a set of questions that appeared in 2025/26 edition of Southeast Mathematics Olympiad. Question number 3, question number 25, 31, 69, 88, and 113. These questions are classic Olympiad Modular Arithmetic questions. The examiner here is not testing your ability to calculate high powers, but your ability to identify repeating patterns, that is circles, and apply Fermat's little theorem where appropriate. Let's go. As usual, I want to first consider the hidden Olympiad principle behind all the 6 questions. Number 1 is to look for the repeating circles of powers before calculating. What do I mean by the repeating circle of powers? Take a close look at the table here. You will discover that the last digit of the powers of 2 repeats in a circle. 2, 4, 8, 6. And the length of the circle is 4. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. 2 to the power 4 is 16. After that, the circle starts afresh, the last digit. The same is applicable to 3. We have 3, 9, 7, 1, which means the length of the circle is also 4. For 4, the length of the circle is 2, 4 and 6. 4 to the power 1 is 4. 4 squared is 16. 4 to the power 3 is 64. The last digit for repeat, which means the length of the circle for the powers of 4 is 2. For 5, every power of 5 ends with 5. The same applies to 6. For 7, the circle is 7, 9, 3, 1, which means the length of the circle is also 4. 8, the length of the circle is 4, and 9 is 2. So let's take note of this, because that's part of what the examiner is testing you on indirectly. The next principle is to reduce the base modulo of the divisor whenever possible. Now this simply means to replace the base by its remainder whenever divided by the divisor before doing any calculation. This works because the numbers that have the same remainder when divided by a number behave the same way in modular arithmetic. Look at what I mean. If I have 13, it is equivalent to 2 modulo 11. 13 is equivalent to 2 modulo 11, which means both 13 and 2 in modulo 11 behave the same. So instead of working with 13 modulo 11, I'll work with 2 modulo 11, which is a simpler, smaller number to handle. Let's go ahead. The third principle to take note of is the use of Fermat's little theorem whenever the divisor is a prime number. When the divisor is a prime number, there is need to use Fermat's little theorem. Fermat's little theorem states that a to the power p minus 1 is equivalent to a modulo p when p is not equal to a, and if p is a prime number. So we're going to apply Fermat's little theorem when we solve some of the questions. It doesn't mean that all the questions test on the same thing, no, but we need to take note of this. Another principle is recognizing the obvious divisibility. What I mean by obvious divisibility is that if the divisor is already a factor of a number, the remainder is 0. Remember that in modular arithmetic, our interest is the remainder. That's why we call it remainder arithmetic or circular arithmetic. This means that if I raise any number to any power and divide it by the same number, there will be no remainder. If I raise 5 to the power of 4,343 and divide it by 5, the remainder will be 0. Please take note of this. Never attempt to compute enormous powers directly. Olympiad questions reward recognizing their underlying pattern, not performing long calculations. These are exactly the kinds of hidden mathematics that competition problems are designed to test. Your ability to recognize an underlying pattern, not just to calculate, get involved in computing enormous calculations and powers. Let's now solve the first question. Question number 3 says, find the remainder when 2 raised to the power 371 is divided by 10. Now, we first of all recall that the last digit of the powers of 2 repeats in a circle and that the length of the circle is 4. I explained that with the table before, which means after every 4 powers, the last digit repeats again. What do we do then? The step 1 is to divide the exponent by 4. Don't ask me where the 4 came from. 4 is the length of the circle of the powers of 2, the last digit powers of 2. Please take note of that. So if I divide 371 by 4, it gives me 92 remainder 3. I'm interested in that remainder 3. Then step 2 says, since the remainder is 3, it means that the third number in a circle, it means the third number in that circle, 2, 4, 8, 6. 2 to the power 1 is 2, to the power 2 is 4, to the power 3 is 8, to the power 4 is 16, to the power 4 is 32, 2 has repeated, to the power 6 is 64, 4 has come. So the third in that number is 8. What this means is that if I raise the number 2 to the power 371, the last digit will be 8. If I raise 2 to the power 371, the last digit will be 8. And we know that whenever a number is divided by 10, the last digit is the remainder. Divide any number by 10, the last digit of that number is the remainder. So 8 is our answer. The next question is very much similar to the first. Question number 25 says, find the remainder when 7 raised to the power 268 is divided by 100. Recall again that the last digit of the powers of 7 repeats in a circle and the length of the circle is 4. So we'll divide the exponent 268 by 4, and that gives us 67 without a remainder. Without a remainder. So because 7 raised to the power 268 divides perfectly without a remainder, it means that 7 raised to the power 268 and 7 raised to the power 4 has the same last digits. So 7 raised to the power 4 is 2401, which means the last digit is 01. And again, you recall again that when you divide any number by 100, the last 2 digits is the remainder. Check it out. If you divide any number by 100, the last 2 digits is the remainder. Now what this means is that 7 raised to the power 4 is equivalent to 01 in modulo 100. So our answer, final answer is 1. The next and the last question I'm going to take is question number 69, which says find the remainder when 7 raised to the power 442 is divided by 7. This should be the easiest of the series of questions because the examiner here is not expecting you to write or do any calculation. He just wants you to recognize obvious divisibility. That if a divisor is already a factor of the number, the remainder is 0. Put the other way around, any multiple of the divisor has a remainder 0. Since 7 raised to the power 442 is exactly divisible by 7, the remainder is 0. So the final answer is 0. You don't need to write anything or do any calculation. All right, that's the much I'm going to take. The remaining questions will come in another video. Just don't forget to like this video, share the video, and subscribe to our channel so that when we do other videos, you will get notified. Thank you.